When we talk about AI, it's easy to picture these abstract algorithms, lines of code, maybe even this futuristic thinking machine. But behind every single chatbot response, every incredible image that gets generated, there's a very real, very physical machine, a massive, power-hungry machine. And today, we're going to pull back the curtain on its hidden engine, the network itself.
So let me ask you this. What do you think is the single biggest challenge holding AI back right now? Your first thought is probably, oh, it's raw processing power, right? Or maybe we need smarter algorithms. But the real bottleneck, the thing that's actually slowing everything down, well, it's something you probably wouldn't expect.
It all comes down to this. It's not the software, it's the wiring. Seriously, the physical network that has to connect thousands upon thousands of processors together has become the biggest hurdle to building more powerful AI and building it faster. The problem isn't just about how fast an AI can think, it's about how fast it can communicate.
And that gets us right to the heart of the matter, what we're calling AI's hidden bottleneck. It is all about how these incredibly powerful processors talk to each other. See, every single AI training job, and I mean every one, dances to this basic rhythm. It's called the compute, exchange, reduce cycle. First, a processor computes its little piece of the puzzle. Then, it has to exchange that result with all of its buddies. And finally, they all reduce or merge that new data together. And then, the whole thing starts over. Billions and billions of times.
Now, here is the absolute kicker. That exchange part of the cycle, the communication, that can eat up to half of the entire time it takes to run the job. Let that sink in. For every hour the AI is supposed to be working, these multi-million-dollar processors can spend 30 minutes of it just sitting there, waiting for data to show up. It's an incredible waste of time and power.
As you can imagine, a massive bottleneck like this has kicked off a huge debate in the tech world. It's all about what's the right way to build these networks, and it's pitting two totally different philosophies against each other.
So on one side, you've got a technology you've definitely heard of, Ethernet. I mean, this thing's been around for over 50 years. It's gone from a 10 megabit per second network on college campuses to the 800 gigabit backbone that runs the entire cloud, and now AI. It's the open universal standard pretty much everyone uses.
And this is where the two big ideas really clash. In one corner, you have InfiniBand. It's a legacy tech that creates these isolated network silos. It's really specialized for high-performance computing, but it walls the AI system off from everything else in the data center. The Ethernet approach, though, is the total opposite. It's all about unifying everything, creating one single open network that makes operations simpler and lets you control the whole system in a coordinated way.
Okay, so let's say we go with that unifying Ethernet approach. What does it actually take to build the physical brain for a huge, large-scale AI? Well, get ready, because the numbers here they're just staggering. All right, first up, the processors themselves. We are not talking about a few dozen or even a few hundred. For a single large-scale AI cluster, you're looking at more than 131,000 of them. And every single one needs to be able to talk to every other one basically instantaneously.
So how in the world do you connect all of those processors? You do it with this massive web of high-speed switches. And again, not a handful. We're talking more than 5,000 of them, all just to play traffic cop for the data flying between those processors.
And here's where it just gets completely mind-boggling. The power. Just to run the network, I'm not even talking about the processors themselves, just the network, takes 9 megawatts every single hour. That's enough electricity to power a small town, and it's just for the wiring.
And you got to remember, that insane 9 megawatt number, that doesn't even include the power for the 16,000 servers themselves. It doesn't account for the more than 328,000 individual cables and optics, all crammed into hundreds of racks that fill up a giant data center. The physical scale is it's almost impossible to wrap your head around.
So how on earth do you manage this kind of insane growth and all the problems that come with it? Well, the industry is tackling it with a two-pronged attack, scaling both up and out.
Okay, so let me break down how this actually works. Scale up is all about making the connections inside a single server rack crazy fast, so the processors in there can share memory directly with each other. Then scale out, that's the massive network we've been talking about, the one that connects all of those individual racks together to form one gigantic brain. They're two sides of the same coin working together.
This is all amazing technology, for sure, but it brings us right back to that terrifying number, 9 megawatts just for the network.
So the real question becomes, how do we solve this absolutely massive power problem? Well, one of the coolest solutions is a new piece of hardware called Linear Drive Pluggable Optics, or LPO for short. Basically, by simplifying the internal design, these little LPO devices can slash the power used by those hundreds of thousands of optical connections by up to 50%. At this scale, that is an absolute game changer, both for the electric bill and for the environment.
And the savings don't even stop there. It turns out you can shave off another 10% of the power bill by switching from old-school air conditioning to much more efficient liquid cooling. For the network switches themselves, it's about finding savings at every single level of the system.
Now, these hardware fixes are absolutely critical, but the real long-term solution, that's going to require everybody in the industry to work together. And this brings us to the future of AI networking, which, it turns out, is looking decidedly ultra. And that's where the Ultra Ethernet Consortium, or UEC, comes in. This is a huge industry-wide team-up. You've got network companies, suppliers, cloud operators, all working to evolve Ethernet specifically for the crazy demands of AI. The whole point is to create one single open standard that everyone can use and build on top of.
And believe me, this isn't just a new name. This new Ultra Ethernet Transport, or UET, it completely rethinks how data moves. So instead of that old, rigid, everything must arrive in order delivery, it basically sprays data packets across every possible path to find the fastest route. And if a single packet gets lost, instead of having to resend this huge chunk of data, it just resends that one tiny missing piece. It's smarter, it's more efficient, and it's built from the ground up to handle up to 1 million processors with security baked right in.
So, why does any of this technical stuff actually matter to you? Well, it's pretty simple. It all leads to AI jobs finishing way faster. It means we're using those incredibly expensive processors more efficiently instead of letting them sit idle. And because it's all built on open standards, it drives down costs and gives everyone more choices. This is the foundation. This is what's going to let us build the even bigger, even smarter AI models of the future. Which, of course, leaves us with one final and, frankly, enormous question. AI's appetite for data and for computation, it seems to be infinite. It just wants more and more. But the physical resources we have to build and power its brain, the data centers, the power grids, the raw materials, those are very finite. And the great challenge for all of us moving forward is going to be squaring that circle, reconciling our infinite digital ambition with our very finite physical reality.